13.3, an arc length shortcut. The city of Riverside has two straight highways extending out from its town hall, located at T in the image. Several roads shaped like circular arcs connect the two highways. Exits from one of the highways are shown at points A, B, C, and D. So basically, there are two highways coming out of town like this. This is the town hall. And then as you extend on those roads, I guess if you wanted to connect quicker, if you lived out here, you could get on the highway and then take this exit to get all the way to this point over there. So it looks like a circle. It looks like a partition of a circle. We've got arc length here and different radii creating different arc lengths as well. But we've got sort of a common angle that the two roads are leaving town from. All right, so number one, they want us to create a table that shows arc length of the connector roads as a function of the radius r of the highway. So when they say L as a function of r, they mean L of r, which does not mean L times r. It means function notation, sort of like we've seen f of x before. And all this means is that L is the dependent variable, sort of like y, or what y usually is, and then r is our independent variable. Which is normally denoted by an x. So in this case, they're saying that the arc length depends on the radius. So I'll quickly make my two-column table, R and L, as opposed to X and Y. And I've got, let's see, 1, 2, 3, 4 different rows I'm gonna have. Okay, so the first one is rather simple. We've got a radius of 2 and an arc length of 3. The next one is a little bit tricky. What would the radius be for this arc length here? Well, hopefully you added these two radii together to show that it's in total from T to B going to be 6 units, or 6, does it say how many units it is? Oh, miles, I'm sorry, it says right there, MI. All right, so when it's a radius of 6 miles, that is a length of 9 miles. 6 plus another 5 is 11, so it's 11 and 16.5, and then 11 plus another 3 is 14, and that'll be 21 miles on the outskirts there. All right, next they want us to plot these points. So very important that they told us which variable was a function of the other, so that I know which is my x and which is my y when I graph it. So r is my independent variable, L is my dependent variable. So I'm going to go up to 14 on the x-axis, right? That's my maximum. So let's try and find a good scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it goes up to 10. I got to fit 14, so let's try going by 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Sometimes you don't have to use up all this axis, that's fine. We're going to end at 14. So, I like to keep it simple with scales like 2. This one we're going up to 21. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 spaces, so I might as well go up by 2 and at 22. Great. Now I'm going to plot my coordinates. My first coordinate is 2, 3. Then I've got 6, 9. 11, 16.5. Now it's going to be kind of tricky. 16.5 is going to be like a quarter of the way up between 16 and 18. That's all right. 14, 21. That one is pretty doable. All right, so plot the points from your table and connect them. All right, so let's see. So I actually don't know where we're starting, right? This is the first point I'm given. So I'm going to start from here. All right, and I notice that as I line up my coordinates here, they are actually all going to be collinear. So what does that mean? That means that there is a relationship between radius and arc length that has a constant rate of change. Let's see, would it actually go and hit the origin? Let's just see if it would. And it's pretty close if we were to extend it. So not only does that tell me that it's got a constant rate of change, it's also proportional, meaning that it starts at 0, 0. So there's just a single number that I multiply r by to get L. So we're going to hopefully find out what that missing number is. All right, the point should form a line. Write an equation for this line using the variables L and R. So this is a line, right? So that means we're going to use our formula for a line in slope-intercept form. That's the most simple one we can use. We also have point-slope form. I suppose you could use that. All right, so I don't know for a fact that it goes through the origin. It looks like it does, but I don't want to assume that. So I want to use what they've given me. So they've given me coordinates. That's something I actually know. So the first thing I'm going to do is find slope. And slope is equal to rise over run, or change in y over change in x. So for my first box, my y goes up from 3 to 9, so that's equal to 6. My x goes up from 2 to 6, that's equal to 4. 6 over 4 is equal to 3 over 2, or 1.5, whichever one you like. Now, I think my y-intercept is 0, but I want to prove it. So to do that, I'm going to plug in any coordinate I like in for x and y, or really r and L, but we know that they are the same as x and y. 3 is equal to 1.5 times 2 plus b. 1.5 times 2 is 3. And what we're actually going to end up here is that... Sorry about that. My phone actually ran out of space during the video. So as I was saying, 3 equals 3 plus b. So we subtract 3 from both sides to get b alone. And in actuality, we find out that the y-intercept is 0. So b is equal to 0. So if I plug it back into my formula, I'm just left with y equals 1.5x. In terms of L and R, which is what they want us to use, we know that L and y are the same and x and r are the same, so I can just substitute those in and get my formula. So number 4 asks, what does the slope of the line mean in context of the highways and connector roads? So anytime you're talking about slope, the way to really get a good physical interpretation or real life interpretation of what the slope is to divide the y by the x in terms of its variable value. So my y variable is L, which is the arc length. As a function of radius, which r is the radius, or in this case x, over radius length. So that should look a bit familiar. We have seen arc length divided by radius length before. Maybe it looks even more familiar when we write L over r. If you divide those two, you actually end up with the value for theta in radians. And we can sort of verify that this is true. This looks to be a little bit less than a right angle, correct? So a right angle would be pi over 2 radians. Pi over 2 is about 1.57, which is a little bit more than 1.5. So that's a pretty good estimation. So in this case, the slope is 1.5 radians. It's the measure of the central angle that we see right here. The city wants to build a new arc-shaped connector road starting at point E, which will be an additional 6 miles past exit D. How long will this road be? Okay, so they're asking us to make a prediction based on the formula we've created. L equals 1.5 times R. So they want to make it an additional 6 miles past exit D. So that means an additional 6 miles here, and they're talking about the radius length. So if my last radius was 14, plus 6 will bring me to 20. So L is equal to 1.5 times 20, and 1.5 times 20 is equal to 30. So that would be 30 miles. So what we've actually done is create a formula that gives us arc length when we know the radian measure. We know that it's 1.5 radians for that central angle. So really what we can now say is that arc length is equal to theta times r, where theta is equal to the central angle in radians. So, I mean, why did we do this? I mean, yes, obviously, where you might be given a problem on a quiz or test that gives you radians, so you need to know how to handle it. But in actuality, we've made our lives a lot easier. If you compare this formula with the formula for arc length when we know degrees, when theta is in degrees, this formula is far more complicated than this. We just multiply radians by the radius. Same with our formula for area. Area equals 1/2 times theta times r. That is so much easier than the area of a sector being theta over 360 times pi r squared. Or maybe this one is dramatically more complicated than this one, because this has no fraction at all. So there's more to it than just learning a new unit of measurement. Radians do make our lives a lot easier, and you can see that from these two formulas here, how much simpler they are than the two formulas you have right here. So I mean, you know, it's up to you. Maybe you still prefer degrees and you're always going to convert to use this formula, but if you do feel comfortable with radians, these formulas are far simpler to use. All right, that is all for lesson 13.